Hello and welcome to week 4 of Program Design and Development. This is the algorithmic section of the course. This is part 1. Let's get started. So today we've done all the preliminaries and now we're going to actually look at some data structures and ways of speeding your code up. Today we're going to be looking at linked lists, we're going to be looking at array lists, and we're going to be following a scenario of how you might actually speed some code up. We'll see that for later. Let's get started. So now the one item that you will use at least 50% of your time, it's the list, the array. Yes, you've been using it already, but let's just cover the basics, particularly for those whose Java isn't as strong as it should be. I know a lot of people struggle with this when they begin to program, but hopefully by now you've got it already. Let's just cover the basics. We start off with a variable. A variable is just something to store something, a way of remembering something that you want to keep of later. And quite often people might start off with like name, or I want to remember the name of somebody. Oh, now I want to remember two names, the first person I meet and the second person I meet. Okay, I need name 1 and name 2, and then name 3, name 4, name 5, and believe me, I've seen this in enough student code to make me cry. People just keep on going, and I've seen name 128, and they've literally typed all of those in by hand. And then they just use the variable like it would. So name equals Adam, name 1 equals Bob, name 2 equals this. Now there's a much easier way of doing this in Java and every other programming language, and you probably know this already. It is to create an array. So this is the syntax for an array. Notice the angle brackets around the 1000, and that's the equivalent of saying name 1, name 2, name 3, name 4, all the way up to name 1000, actually name 999 if you realize that arrays are indexed from 0, more of which in a moment. So here we go, and we can just, instead of going name 1, name 2, name 3, name 4, we just put the 1, 2, 3, 4 in a square bracket, and everything works as it has before. Now, one way to think of an array is to think of a very long line of pigeonholes. And what's nice about having this long line of pigeonholes is if you've got code that will handle one pigeonhole, you can imagine a kind of robot arm and a conveyor belt, and it will do everything to every item in that array list. So if you can set things up so it will operate on one, you can do it for many. And this is what a loop does. So we have two types of loop. The loop at the bottom is a traditional for each loop, and that has to know how many times it's going around. And the loop at the top is the for each loop, which makes things a bit simpler. And what it does is, instead of saying names 1, names 2, names 3, it says for some box called, let's say S, let's do this. Okay, enough of the refresher. Let's think about arrays. What are the problems with arrays? Well, the first thing is arrays are typically fixed size. And you get this a lot more in C and C++ because they don't have dynamic arrays as much, particularly C. And so in advance, you have to kind of decide how many you want. And that can often be a problem. It's like, oh, you're making an address book. How many friends have you got? And you will see this in a lot of very junky code. Have you ever been to a place where they've kind of gone, oh, well, unfortunately your name is too long for the list. It only accept names that are like 128 characters long, and yours is slightly bigger, so you're going to have to trim your own name. Yes, that's because the array it was being pumped into was of fixed size. So what's the problem there? Well, you can either make the arrays very big. Oh, I'll make my array for my name 1,000 characters big, but then you're going to be wasting most of that space inside the machine. So a solution was evolved. The solution is called vector or ArrayList. Now it's vector in C++, ArrayList in Java. There was a vector in Java as well, but hey, we're just making life too complicated. Let's think about ArrayList. Inside class ArrayList, there are basically two things. The first one of which is, surprise, surprise, an array. The second one of which is a counter that keeps a count of the number of items used. So let's see this in action. Let's create an array, and this is the hidden array inside the array list. So we create one, and it starts off and it will create an array of size, say 4. It doesn't really matter. And then we add items. We add Bob, we add Dave, we add Chuck. Okay, so far so good. And the count of the number of elements in the array is now 3. And then we add Vince. So the count of the number of elements in the array, the size of the array, is 4. So what happens if we want to add Jenny? At this point, the array list pauses. And what it does is it creates an array list twice as big as the previous one. So if it was 4, it's now 8. Then it copies all the elements over. It copies Bob and Dave and Chuck and Vince over into the new, much bigger array. And the elements in the array going, oh, it's nice and spacey in here. And then suddenly Jenny is added to the end of that list. And the same thing happens until we get to the size where we keep adding stuff and it reaches that limit. So now we've hit the size of the array, which is 8, and we want to add one more person. And in which case, boom, the array is copied again. A new array is allocated, the array is copied, and it keeps growing incrementally like that. Now, that doubling of size, that can be quite wasteful, but generally it's quite a good compromise between allocating too often. So some of the C++ ones would allocate every 4 items. That's going to be a bit of a waste of time. Or allocating too much. Again, if you're in fear of allocating too much and wasting too much space for an array list, you can always tell it how much space you actually want, or you can go trim and it will slim itself down to the array you've got. So hopefully this is all just refreshing, which is why I'm going so quickly with this. So let's have a quick look at some code. Here we go. Here's an array list. Here's the item. We go add, and then the first item we add will be added to the beginning of the list. The second one will be added after the first. Now, the key aspect of every array list is there are no gaps allowed, and we'll come back to this in a few minutes. But it will. So the first one is 0, then the second one is 1, third one is 3. If we ask it how many items we've got, it'll say 3. And equally, once we've got elements in an array, we can use the for each loop to iterate over every item that array list. And to give ourselves a kind of a bit of a mental picture, what we've got is the array list. The object names in this particular case, which is the array list, it internally has this magic array, which we can't see, the hidden array, and the hidden array points to these elements. So when you ask for Julie, it keeps Julie because it's really looking at Julie's phone number, and then it hands you back that phone number, the pointer that gives you back. So far, so good. And I'm quickly going to cover something else, which is about the security features inside ArrayList. So one of the big problems with building very big bits of software is that you end up getting confused with what's in what, particularly if you've got lots of programmers involved. And if you've been working as a programmer in a group, any team project so far, you should have noticed it's going to get complicated and you don't know quite what that array called flogalog is all about. So yeah, using other people's code, it can get pretty messy, and it was one of the points, was one of the kind of sources of great falls over of Java code. So before they invented Java generics, you would basically have an array list, and an array list would accept anything. So I've got an array list S1, and that will accept an apple object, and it will accept a potato object. It will accept anything. You can put any mess inside that thing. And supposing you had an array of apples, you could assign it to an array of potatoes. No problem whatsoever. Now, that might seem a bit trivial in that case, but if you've got a huge amount of software, you're talking about tens of thousands of lines of code, keeping track of all this becomes really complicated. So with Java generics, what happens? You tell it what is in the array. You don't just say I've got an array of stuff anymore. You say I've got an array of apples and I've got an array of potatoes. So apple, potato. So S1 in this case, we add an apple to the array of apples, not a problem. But if we add a potato to the array of apples, it's going to complain. Now you might think, oh, hang on, this code is complaining more than it used to. Is that good? Yes, it's very good because that's stopping you having a bug later on. The other thing it stops you doing is assigning a variable holding one thing to a variable of another thing. So for example, supposing you had an array of windows and you wanted to assign them to an array of fish. Now with old-fashioned Java, that was completely acceptable. If you're using Python, that's completely acceptable. But with modern Java, with generics, that's going to be caught early on. And that's the big advantage of using these kind of modern languages. Let's just quickly go over and revise arrays and array lists. They are very similar in many respects. Arrays can hold primitive types. Array lists can only hold primitive types stored in objects. Array lists can only store objects, basically. So to create one as an array, we go new int square brackets the number of elements we want. Remember, we have to tell it the fixed size of the array. Array list, we can suggest the size of the array, and that's what the 100 and around brackets does. But before that, we just have to say, I want an array list integer, and I can put 0 in that 100, and it will just like keep expanding as it needs to, unlike array. Again, if you add too many items to an array, it will then crash. You can ask array in a very weird syntax to actually say, how big are you? And all that does is it gives you the 100 that you told it to begin with. So you don't have to hang on to how big that array is. You can actually just say, array, how big are you? That can be quite useful. With an array list, you just say size. It's a method to the object. You just say, how big are you? And remember, it's not telling you how big the array is, the invisible array. It's telling you how many things have you got inside you now. The next thing you can do with an array is you can assign to it. So you can say you can add an element to the array. And the only way of adding an element to an array is to assign it to a particular location. So you can say element 0 is equal to 5. Now, initially when you create an array, it's full of zeros or nulls depending on what you've put into it. It will accept that. And you can have an array with emptiness in it. It's kind of like having broken teeth where there's some missing. And the array is perfectly fine with that, and that can be quite useful. An array list, they all have to be lined up with no gaps in. So when you add to an array, you just assign an element to a location. When you add to an array list, you can say, oh, add 5. And what it will do is it'll add that to the end of the list of items. So if there's 10 items there, the 11th item will become 5. To get an item out of an array, that's very simple. We use the square bracket syntax to dereference the second or third item in the array. And the object equivalent of that with ArrayList is get, and that will just return that item in the array. Again, in both cases, you cannot ask for an item that's too big. I goes on the end of the array. If you've got an array of 100 items, you cannot ask for the 100,000th item. It will crash. And again, we can set a value in an array. That's just an assignment. In ArrayList, that's set. And if there's another item in array item 3, if there's another item in array value 3, it will get overwritten with the value you're putting in this case 56. Both ArrayList and array understand the for each syntax. And that's when array starts to look slightly old-fashioned and dour, because ArrayList comes with a whole bunch of really useful, handy methods. The first one of which is insert. And what insert does is it basically is kind of like inserting with a cursor, or imagine you're in a queue and you're the third person and someone turns up, a friend, and goes, can I join with you? Can I squeeze in with you? And then everyone on the back of the queue has to move back slightly. Also, you don't have to write a for each loop to find something. If you want to do a search, a find inside an array list, you can just call index of, and that will tell you the index, the location in the array of that particular item. If it can't find it, it will return -1. That saves you a lot of just typing code, which you would have to do in Java or C, for example. And again, if you want to get rid of items, you can go clear. Now, what's quite clever about clear is it just kind of resets the item count to 0, so it's incredibly fast, but it hangs on to the original array. So if you're filling up that array again, it doesn't bother reallocating the size of it. It's already filled up. So let's go through the ArrayList methods just quickly. We've got allocating an array, getting the size of an array, adding an element to an array, adding an element at a specific position. This is like assignment. It will move things up to kind of insert it. We've got getting an element. We've got setting an element. It's just getting it back. We can even remove an element. You can just say get rid of item 5 and it will just go away and do it. You can say clear and that will get rid of everything. And if it's empty, you can just say to the array, are you empty? And it goes, yeah, I've got no elements in myself. And finally, we've got index of, which I've told you before is like searching for something inside that array. So let's skip over this demo. But I'm going to point out a couple of elements which I've said before. There are routines that can be associated with arrays and array lists. In this particular case, we've got sort. You give it an array of primitive items like strings, it will just sort them for you. So you can call collections.sort with your array list. But you can also call shuffle, and shuffle is the opposite of sorting. It will basically put it together randomly. And if you think that's easy, try writing it yourself. So, part 2. Let's have a look at some of these elements in depth. Let's look at some of these elements in depth. Let's look at removing an element. I said that was a utility that ArrayList gave you, and it's pretty useful. Let's see how it actually works, and let's see how fast it is. So here we go. We've got an array, one with just numbers in this particular case. Could be strings, could be fish, could be apples, we don't care. And we've got 1, 2, 3, 4, 5, 6, 7. And we remove item number 2. So the first thing that happens is we just set item number 2 to null. So there you go, it's gone. But remember, ArrayList doesn't like having gaps. So what it does is it moves the item above into that gap. But then it's made another gap. So it moves the item above into the gap again. And it keeps going, moving up, bubbling up until it reaches the end of the array. So let's try and revise last week. How fast is this code? And to really say how fast this code is, we really say how scalable is this code? So what's the O notation for the code? Can you ever think now? Okay, let's look at this in a bit of a slow detail, but we'll go through the details. So how do we work out the order n of this? Well, the first thing we need to do is kind of sketch out what the code for doing this would look like. So here's my sketch. To remove an item from position X, starting from position X and up to the end of the list, move the item in position X plus 1 into position X. Keep going until you reach the end of the loop. So what order is this pseudocode? Well, remember, the advice I gave you last week was to count the number of loops. How many loops do we see here? Yes, we see 1 loop. So this is going to be roughly order n. Now, you might be sitting there saying, well, it's not always going to be at the beginning of the list. But remember, it's on average, it's going to be half the size of the array. So on average, it's going to be n over the 2 items to be moved forward. So that's, now remember, we don't really care about 2s. We only care about n. So that's order n again. So it's going to take order n to do this. Think about it this way. If you double the size of the array and you're removing an element from it, you're going to have to remove twice as many items. So it's proportional. It's order n. Okay, so we know that remove is order n. Let's have a look at a slightly more complicated case of insert. So insert takes 2 arguments, where to put it and what to put it. So we're going to insert at item 2 again. Oh, but the problem is this item 2 is there already. Remember, if we wanted to replace item 2, we'd use set. Insert keeps everything there. So what do we have to do? We have to move things up. So we move the 7 up to the top, and the 6 has to move up, the 5 has to move up, the 4 has to move up, the 3 has to move up, the 2 has to move up, and finally we have the space where we can write the element we'll take. And finally we have the space where we can put the element we want to insert, in which case this case is 90. And again, that's the same. It doesn't matter if it's an array of windows, an array of strings, an array of hats. We don't care. It will operate in exactly the same way. They all have to be moved up. So how long will this take? Remember, we don't really care about time. We care about scalability. So what is the order of this? So let's quickly sketch out the code again. So to insert an element E from a list, an element E into a list. Oh, there's a good syntax error for you there. We start from the position X and we go up to the end of the length of the list. So what we're doing is we're going through and looking for the element E. So let's have a look at the pseudocode. So to insert an element E into a list, not from a list, there's an error. So how do we do this? Well, the first thing we have to do is find the element we want to remove, don't we? So we're going to start from the beginning, 0, and we're going to go up to the end of the list. It's got to be within there somewhere, and if it's not, we just won't remove anything. So let's start from 0 and we go up to the end of the list, and if the item is at position X, we just remember where the X is, and then we break the loop and we skip out. So that's the first part, and then from position X to the end of the list, we move from the end of the list down to position X, we move all the items up there. So what order is this? Now remember, we're looking for 4 loops here. Let's count the loops. I count 2 loops. So the first loop here is the first for loop doing the searching, and the second loop here is the loop going from the end back to the beginning looking for that particular item. So the first item is order n, the second item is order n. So we've got 2 order n's here. Now remember from last week, if an n is followed by an n, that's just n plus n. And that gives us 2n. Now remember, we don't get out of bed for 2's, we only get out of bed for n's. So basically, it's going to be order n. And again, think about it in terms of scaling. If we make it twice as big, it will take twice as long to actually do the removing. So, in this case, so remember, if it's twice as big, it will take twice as long to do the inserting. So insertion is order n. So you're thinking, why is he wasting all my time with these minor details? How is this going to make my code go faster? Well, let's cover that in the next section. Part 3. How to speed up programs. Now, we're going to use a scenario here. And the reason I'm using a scenario is basically to show you what actually happens in a real world kind of situation. The thing is, I cannot tell you what to do. Right? Speeding up code needs common sense. There is no simple formula. It's about improvising, measuring, following hunches. It's more like being a detective, and I cannot create that into a simple press this, do that, do the other formula. You have to really intuit what's going on. It's all about applying your thing. And in fact, it's ultimately about thinking. And that's why we teach computer science at university, not as a apprenticeship course. So let's start with our scenario. You've gone to some swanky meetup.com and you've bumped into these guys who are building yet another lovable dating app. Now, it doesn't matter that it's a dating app in this particular case. This could be a COVID app for all I care. Basically, they've got a problem. And you're chatting with the guy and he goes, the problem is we have this dating app, but the problem is it sucks. And it sucks because it uses up battery like crazy. And you're saying, well, what does this app do? And the guy goes, oh, it's really clever. What it does is, as you walk around, it links up with other people who have the app, and it gives you a list of everybody who's closest to you who's actually being up for dating. So it kind of, it gets you dates within your kind of nearest radius. So let's have a look at simulation of that. So as you walk around, your phone is constantly talking to other phones, and it's constantly updating that list of who's near you and who's closest to you. And of course, what they wanted was, as soon as a new person arrives, we want that new person to be at the top of the list, because you probably know what's on the rest of the list by now. So if we look at the individuals, basically we have a number of people who are close to you and people who are beyond you. So what do we do now? If you remember last week, the first thing I did was teach you to think about what is the big N. because the big N is going to cause the scalability problem. It's probably causing the problem now. They've got a lot of code, and you don't want to waste your time trawling through all of their code, looking at every minor inefficiency. It's like, oh, your sports car, your Formula One sports car isn't going as fast as the other one. I'm not going to look at every piece of metal in that entire engine trying to figure out how to make it go faster. I'm going to be smarter than that. I'm going to be looking like a detective, trying to detect the problem. So the way we start is, what's the big N? And what's the big N in this particular app? You might be sitting there and you might have put your hand up and said, oh, well, I think it's the number of users of the app. That's going to be the biggest number, isn't it? But your app doesn't contain every user. Your phone does not contain every user. They're going to give you local users. Facebook doesn't download every person in the world onto your mobile phone app. It only downloads the information you're interested in. And this app's doing the same thing. So the number of clients worldwide isn't the big N for this particular problem, because the problem is on the app. If it was a problem with the data server centers, that might be different. The guy definitely said it's sucking energy out of the phone. So we know the problem is somewhere on that app. So the big N in this particular case is the number of people around you. So now we've decided what the big N is, we can then start saying, what are the data structures that use that big N? So we begin to investigate, and we trawl through the code, and we discover that, well, there's only two places. The big N is basically an array list called potentials. Yes, this is a bit of a setup, isn't it? The array list is called potentials, and it gets created, but it only gets created once. That's not going to be a problem. And then as the person's going around, we're getting these two calls. And I've, again, simplified the code to make it easier for you to read. There's one that is called update new. And what it does is, if a new person is discovered, it basically adds it, inserts it into the array. But it inserts it at the beginning. And later on, if someone's too far away and it's lost radio contact via Bluetooth with the other person, it calls the remove function on the array list. So what's the problem? Think about that for a second. Try writing it in your notepad and into the system if you have it. And let's start up with the next slide. So the problem here is the array list is slow, and the removing from the array list so the problem here is inserting into the array list is slow and removing from the array list is slow. Problem over, you say? Yeah, but what else are we going to use? This application is, so the problem here is inserting into an array list is slow. Okay, it's order n. And removing from an array list is slow. It's order n. And this application is doing these updates every 10th of a second. So the reason it's doing all these updates is it needs to keep track of all these things. It's doing a lot of work on each update, and that's what's draining the battery, probably. But what's the alternative, says the other developer. I have to use an array list, don't I? I mean, what else am I going to use? It has to be an array list or nothing. I mean, there's nothing else that's going to do the job. So let's move into part 4. Part 4. Solving the problem. So we haven't covered linked lists so far, but if you knew about our linked lists, you would realize they could actually be the solution to the problem. So the first thing we're going to do is we're going to look at how an array list, a linked list is created. So the first thing we're going to do is look at how a linked list is done, and then we're going to actually see how fast they are. So ultimately, what we're looking for is a kind of an array list. It looks like an array list, but it's cheap to insert at the beginning because the new person has to be at the top of the list. And we need a cheap way of removing the element. We don't iterate over that element much, and we don't get an indexed item much. Now, if you've gone away and read the book, you probably already realize that maybe what we need to use is a singly linked list. What is a singly linked list? Think of it as a chain. It consists of a sequence of nodes. each node is connected in one direction only. When I'm teaching this live, what I do is I get some of the students down onto the stage in front of me and we form a physical linked list, because everyone's got one hand and they have another pocket with data in it. So a singly linked list contains a link to the first node. We'll see how that works in a minute. So here is our singly linked list, and it begins with and it stores 2 items in each node. And the node basically has one item, which is the data structure, it's the payload, and it has a pointer to the next item. It's got a reference to the next item. I think this looks better as code, so let's have a look at it as code. Here we go. So we've got a class link. It has the data, and it has the next link. It points to itself. And that allows us to create this chain of items. So let's have a look at this. Let's have a look at drawing. This is very simple. This is drawing. This is very simple. So here we go. We start off with the root. I am root. And root points the list. So the first item in the list basically calls draw. So it basically says heady.draw. And then it sets the item in the list. So this is our pointer, this one, and it points that to the next item. So it gets the next item in the list, and that becomes Bob. So then it prints out Bob. And Bob gets printed, and then it sets this one to Bob's next, which is Jenny. So then it draws out Jenny, and then it says, oh, get the next one. But the next one is null, because Jenny is at the end of the list. So it loops while the next one is null. It's not looped, so it finishes out. Okay, so far that should be pretty straightforward. And if you're having problems, remember, don't forget to check the textbook, and there are a couple of other animations available. So let's insert into the list, and there's a couple of places there are a couple of scenarios we need to think about the inserting from. We can insert from the head, we can insert from the tail, and we can insert somewhere in the middle, and we can insert while the list is empty. So let's have a look. Let's insert at the head. So what we've got is our list. We begin with root. Okay, I am root. I'm pointing at Heady, who's the first person on the list. Heady points at Bob. Bob points at Jenny. And I want to insert Rockwood at the head of that list. How do I do this? Well, the first thing I do is I make Rockwood point to Heady. So Rockwood points to whatever root is pointing at. And then I make root point to Rockwood. So how complicated is that? Well, I do one operation and I do another operation. So inserting at the head of an array list is O of 1 plus O of 1. Well, that's O of 2. And O of 2, well, we don't get out of bed for 2. It's O of 1. So it's always O of 1. No matter how long that list is, like it can be a million items, I need to do 2 operations. So think about this. I make the array list twice as big. It still does the same amount of work. I make it a million times bigger. Inserting at the head still does the same amount of work. Oh, this sounds pretty interesting. Let's have a look at something else on ArrayList. Let's have a look at something else on LinkedList. So let's insert an item at the end of a linked list. How do we do this? So we want to insert Rockwood at the end of the list. So we begin with a root, and we have this thing called a cursor. It's kind of just pointing at an item in this array list. We have a pointer, a cursor pointing to the item in the list, and we begin with root, so it points at Heady. And it says, Heady, have you got a tail? And Heady goes, yes, I have got a tail. So I basically update my cursor to point at the tail of Heady. There we go. And then we say, Bob, is your next empty? No, it's not. So so we make the cursor point to whatever Bob's pointing to, which in this case is Jenny. And now we say, Jenny, are you empty? Is your next empty? And he goes, yes, I am. So what you do then is you basically say, okay, we've found the end of the list. What we do is we update Jenny's next to being Rockwood, and we make sure Rockwood's next is null. And so now Rockwood is at the end of the list. Now, how long is that going to take? Well, if you notice, we had to go into a loop. So that's going to take O of n. So to insert at the end of a linked list is going to take O of n time. Literally, I mean, it's going to take as long as a list. What about inserting in the middle? So let's say we have to find an item and we want to be in front of it. So again, it's like inserting. We start with the root and we point at heady. So our cursor points at heady. And then we say we keep walking down until we find the item we want. So here we go. We found that we want to insert before Jenny. So the first thing we do is we make Rockwood point at Jenny. And then we copy Rockwood's cursor to next, yes. And then we make Bob point to Rockwood. So what we've done, we've inserted Rockwood into that list. So if we're inserting, say, the 12th item, and our list is, say, 10 trillion items long, it's still only going to take 4 inserts to get to it. But if we don't know where in the list we're going to insert, it's going to be order n for the size of the list. So inserting into a list at any point in the middle, if we don't know where it is, will take O of n time. If we're going for a specific location, like the 5th item all the time, it will take O of 5, which is basically O of 1. Okay, so the only real problem now is what do we do if the list is empty? So our root points at nothing. So what we do is, if the root points at nothing, we just make the Rockwood point at it. So inserting at the head is easy. And again, that's going to be O of 1 if the list is empty. So at this point, I normally ask, I like my code to crash. What are dangerous things to do with an array list? But we're going to skip that. So, part 5, one data structure to rule them all. So as you've seen, a linked list and an array list do the same kind of job. They both store things in an ordered sequence. But if you notice, the linked list is fast at some things. So for example, inserting an item into a linked list, like near the head or at 0, is really fast. It's order 1. But for an array list, it has to move all the elements. If you're starting from the beginning and you want to insert it the first item, for a linked list, it's instant. For an array list, it has to move all the elements up 1. So adding at an array list, well, adding at item 0 is really fast for an array list. Adding at the end of an array list is really fast. It only has to go to the far end. That's really good. If you add somewhere in the middle, then it gets problematic. The for each loop in both cases takes order n. And the thing is, you're looping over all the n items. It must take order n. And removing from the beginning of a linked list, that's really fast. But removing from, the end or the middle, that's going to take order n. But for moving from an array list, particularly from the beginning, that will take order n. So what we've got is two things that go similar. So what we've got is two things which work in a very similar way, but they're faster and slower than others. Now at this point, I get a lot of problems in the workshops, because in the workshops the students are going, oh, so the way to speed up code is to get rid of ArrayList and replace it with LinkedList. And other students are going, no, get rid of LinkedList and replace it with ArrayList. And they're kind of going, well, you can't both be right. And the answer is, you have to be sensible about it. It's a bit like playing top trumps, if you've ever played top trumps. There is no perfect card. It's a bit like playing poker. There is no perfect card. There is no card that wins every time. It depends upon the context. And the important part about programming is figuring out which context you're in and which of these data structures would work. So we're sitting there with the programmers in the app. They're going, oh, okay, so we should not use array lists for this particular case. We should use linked lists. Is that right? You're going, yes, you should use linked lists. And they're going, oh, But, you know, it's really tricky. We're going to have to go through all of our code, update, you know, instead of declaring the people list, instead of declaring the people list as array list of people, we're going to have to say, oh, it's now a linked list of people. And what happens if we change the code and we discover that actually it's not any faster? We're going to have to change that all back. That sounds like a lot of work. Gee, they say, wouldn't it be great if linked lists and array lists had the same methods and we could just swap them out? It's kind of like having an engine, and you pull one engine out and you pop another engine in, and if the components are modular, they will work. I mean, they're very similar. They both have an add, an insert, a subtract, a remove, all these items. So in fact, there is. And this is an important element of software engineering. Basically, linked list and array list are actually implement the same. Linked list and array list implement the same as we call interface. There is a superclass to linked list and array list, and that's called list. So list is an interface. It just describes how things operate. And it has a list of items, but we don't really care if it is an array list or a linked list. So that means only when you allocate the list, we can actually say allocate a linked list, allocate an array list, which is really nice, which means we can actually swap one out with the other. And if something isn't working, or we realize we need a better data structure, we can swap it in with another one. And then suddenly all the code, no matter if it's a million lines of code, it will still swap in automatically. So here are the links to the Oracle dataset sites for the list, array list, and linked list. So list is an abstract data type. So that's a term we're going to use today, abstract data type. So ArrayList versus linked lists. An array list uses an array for internal storage. That means it's fast for random access. Get me element 99, because it's an array index gets you to the right element. Adding, deleting at the start or the middle of an array list will be slow. Only adding at the end of an array list is fast, because all the elements have to be moved around. That's all order n work. Okay. An array list will also give a performance issue when the internal array fills up. So again, if you happen to add an element, you actually see if you're adding elements and timing them, they won't all take the same amount of time to add. A linked list is made up of a chain of nodes. A linked list is made of a chain of nodes. Linked lists are slow when it comes to random access. If you ask for element 55, it's going to have to walk through the array to get that item. That can be really bad. And that's why we don't use linked lists for everything. Accessing an element, inserting an element, these can be incredibly fast. So for inserts and deletes everywhere, a linked list is quite fast, since all you have to do is update the next and previous pointers. Okay, so we're kind of there. What have we looked at today? We've looked at array lists. We've looked at linked lists. You've seen your first abstract data type as well. So finally, I want to ask you, on your slips of paper, or rather on the reference system, on the note system you've got in front of you, hopefully, I want you to write down one thing you've learned today. And if there's anything you don't understand or would like to clarify, write that down as well. Hopefully we can overcome this whole kind of remote lecturing problem business. Thank you so much. That is the end for this week, and I look forward to seeing you next week.